The views expressed on Skeptically Speaking do not necessarily reflect the opinions of the University of Alberta, the Students' Union, or CJSI.
Good evening, listeners. You are now tuned into the vibrational frequency we like to call Skeptically Speaking, the unique hour-long wavelength where we connect to our listeners, asking them to call in and question everything. So, take off your tinfoil hat and get prepared to dial in, because Skeptically Speaking starts right now.
Hey, Sean. Welcome back, everyone, to your favorite skeptical call-in talk show.
It's actually my second favorite.
Is there another that I'm not aware of? Because we researched
Well,
this.
that makes us the second, the third, the fourth, the fifth.
Your very favorite skeptical talk show.
Oh, we're talking about skeptical talk shows. Then yes, it is my favorite.
Moving on tonight's episode, we'll be speaking to author and prolific blogger Phil Plait, the wonderful Phil Plait, about astronomy. But before we get to that, we have Mike Harrison here for Speaking Up.
Hello.
For your first-time listeners, Speaking Up offers local skeptics and skeptics from around the world a chance to talk about whatever topic they'd like for about 5 to 10 minutes. Welcome, Mike.
Hello.
And
Thank you.
so you'll be speaking today about decoding antiquity.
Basically we're talking about languages that we still can't read, which actually it turns out there's quite a few of them. It's kind of an interesting subject. To start us off, the oldest writing that we know of is Sumerian cuneiform, so, hieroglyphic type stuff, very symbol based. It's found on wedge-shaped clay tablets. It's about 5,000 years old, and it comes from Mesopotamia, which is in the Middle Eastern areas, as I'm sure you're aware. There's of the scripts that we're going to be talking about here, most of them are around that age, and basically they fall into a couple different categories. There's scripts where we have the actual language, like we have the characters and such, but we don't know how the characters are put together, and there's a couple of these. There's ones where we have characters that we're unfamiliar with, and we don't know how they're put together, or we know how they're put together, but we're not familiar with the characters. So we have some, grammatical rules that have survived, but we have nothing else. And then there's the third category where we're not familiar with the symbols and we don't know how they're put together. We have some success decoding the first two, not so much success with the third one.
Give me some examples.
Well, the first one we have is called Etruscan, which is... The Etruscans were a prehistoric civilization in western Italy. They were assimilated into the Roman Empire at about 1st century BC, and their origins might stretch back to about 800 BC, although it's kind of unclear. What's really neat is that the Etruscan artifacts are inscribed in Greek, which was likely borrowed from Greek colonists that seemed to be around the area at the time that the artifacts are dated for. And it's written in a form of the ancient Greek alphabet. But it's not Greek. It can't be read using Greek rules, and we still have no accurate translations for it. This is not surprising because Greek has been around in Europe for about 4,000 years and has a million different dialects. It's actually the most commonly spoken language as a language family, and it's been spoken for the longest. Oh, sorry, not the most common anymore, but has the longest history as a language. So we can languages like this we can read. Sort of. We can recognize proper nouns from their Greek references, and some of the phrases that it shares with Greek we can identify and we can pick those out. But we can't really tell what it means. We don't really know how it's supposed to sound either. It's like I said, it looks very similar to Greek. The biggest difference is probably it's written right to left, so all the letters are pointing in the wrong way. And like Basque, Etruscan is not really related to any other current language. There may be a common ancestor with other Greek languages because they have similar characters, but we've never found that language. We don't know what it is. As far as we're aware, it's not really related to any language that we're familiar with.
So what are some of the theories?
Well, there's probably a root ancestor language. I mean, that's one way to look at it. It's possible that different groups exchange symbols and ideas to build their own languages around that time. There's also there's geographical similarity that implies more than just people have only so many ways to, stroke into clay. But that's basically they figured there was some sort of cultural mixing, but they're not really sure where. It doesn't seem like it all comes from the same place. So it's really interesting, just the way they've developed along different paths. Just for interesting little thing, we have about 250 Etruscan words translated, which might seem like a lot, but by comparison, there are about 600,000 words in the English language, so it's not really enough to go on at this point. Second really cool one are called the Meroitic hieroglyphs, which come from this really interesting time in Egyptian history where Egypt was ruled by the Kushites. Now, the Kushites were a civilization that controlled much of sub-Saharan Africa. They were also known as the Nubians. So you may have heard that reference before. The Greeks and Romans called them Ethiopians for some reason. They never called themselves that, but the Kushites invaded Egypt at around 712 BC and actually ruled the country for about 70 years, and they actually became the 25th dynasty of Egypt. We don't know as much as we'd like to know about them, but it's really interesting. We've just discovered some very large-scale gold factories that were obviously Kushite, which really ups our estimation of their technical sophistication. Kushite, or the Meroitic hieroglyphs that we know come from the Kushite pharaoh dynasty. There's two different languages that make them up. One is a hieroglyphic language, very much like Egyptian that we're familiar with. But like Egyptian that we're familiar with, there's a second dialect that's called cursive, in which characters are joined and they make words or something like word. Exactly, something like that.
So do they have any idea? Were they used for two different purposes?
Well, the hieroglyphic ones were usually used for ceremonial purposes. They were inscribed on monuments and things like that. The cursive stuff was obviously used more commonly. It would have been much easier to employ because you always had to have a specific symbol for whatever you were talking about in the hieroglyphic language, right? There's about, let's see, I had a number for this. There were hundreds of hieroglyphic characters, but there's only about 23 different cursive symbols. So we know they was used some way analogous to language. But even though we can take languages that look similar to it and we can sort of infer how it's supposed to sound. In fact, we have a very good idea of how Meroitic is supposed to... Meroitic. Sorry, it's a very hard word to pronounce. We have a very good idea of what it sounds like, actually, because it's very similar to some other languages in terms of phonetics, but we can't guess at what it means. So it's interesting that we have we can probably imitate it. But,
so, we could, for example, if the word chair was written down, we could see that it was CHAIR, but we would have no idea what a chair was.
No, but we'd be able to say chair.
Okay.
Yeah. And the next ones, there was a lot of different languages in the Mesoamerican area. The first Mesoamerican civilization was called the Olmecs. And they held territory near the south coast of the Gulf of Mexico sometime between 1500 and 400 BC. And they were thought to be illiterate until the 1990s when someone found an inscribed stone block dated to about 900 BC. It has 62 different symbols, some of which are repeated. It appears to be writing, but there are no other examples ever found. Unfortunately, this is the case with a lot of the cultures around there. There's just not a lot of archaeological evidence that has survived, mostly because cultures have been around in the same area for so long. But the Olmecs were best known for their very large, you've probably seen them, they're giant stone heads, very much like the Easter Island heads, in that they're large and stone, but actually very, very round. So not like the Easter Island heads, but I digress. Also have the Zapotecs from a similar region. We have lots of samples of their writing. It was painted on architecture, carved into pots and other objects, dated somewhere between 400 and 600 BC. And we know actually that the Mayan calendar was based on the Zapotec calendar. It was basically directly drawn from there. And unfortunately, that's about all we know of the Zapotecs. We know that the Zapotec language survived and became incredibly diverse. There's many different dialects that are obviously based on Zapotec, but even so, we can't regress them enough. They've all diverged so much that there's no common principles between them.
Wow.
Yeah.
Okay.
Yeah. Last, from the same region, we have Isthmian, which is... No, sorry. Man.
If everyone could see how hard he's trying to pronounce these words,
it's very hard. It's harder than but this language is highly debated. We only have 2 examples of it. One is a single jade statue that a farmer found in his field in 1902. Has about 70 interesting-looking symbols on it, and obviously we can't decipher them. We found another, a larger slab, a 4-ton slab of basalt, with a great deal of text on it a couple years later. And they're both dated to about the 2nd century A.D., and it's likely a version, an archaic version of Zoroquian. Zoquian. I'm sorry. Which is, again, a current language of the area.
Okay, so you're telling me that we're trying to figure out, well, not me personally, but others
These
are trying
people,
to figure out entire languages from, for example, one statue or like a piece of driftwood.
Oh yeah, I mean, well, a lot of the times they will have they'll have a lot of examples of the script, but they don't really have anything useful to reference it against, right? Like many examples of the script, if they don't have anything else, no dictionary, anything like that, no clue as to what the text is supposed to represent, it's very difficult for them to infer any sort of meaning from it. They basically have to look at languages in the area, look for similarities between the characters, they look for, possible similarities between grammatical rules and things like that. But the problem is grammatical rules and such developed greatly over time. It used to be that mostly everything was written basically right next to each other, in a very cuniform type style. Mm-hmm. In fact, there's some really interesting ways of reading these, like Rongo, which I was going to talk about later. You actually, to read a Rongo tablet, you actually start at the bottom left-hand corner, read along the line, then you actually flip the tablet by 180 degrees and start reading the line right under that. And then you do that every time you read a line.
That seems unwieldy.
Doesn't it? It seems very impractical. But this is it was actually reasonably common. Like it's common enough.
But maybe again that could be used in ceremonial kind of things. Like that was part of the movement of the ceremony, was switching the tablet.
It's possible, and that's a good explanation for it. It's really the only explanation I can think of. Next, I
think actually no time for a next.
Okay, well, fair enough.
Yeah. All right.
Okay, well, thanks very much.
Thanks very much, Mike.
Thank you, Mike.
So next, it's on to Astronomy with Phil Plait, right after this commercial. Skeptically Speaking wants you to question everything. To be a part of the discussion, call in every Friday from 6 to 7 p.m. Mountain Standard Time at 780-492-2577 extension 1. That's 780-492-2577 extension 1. You can also email your questions and comments before or during the show to live@skepticallyspeaking.com, or if you're on Twitter, we're at Skeptical Radio. After the show, continue the conversation on our website at skepticallyspeaking.com or check out our Facebook group. You can also subscribe to our podcast on iTunes. Skeptically Speaking is also rebroadcast on Public Reality Radio, WPRR 1680 AM in Grand Rapids, Michigan, Citywide LP 99.1 FM in Madison, Wisconsin, and on freethoughtradio.com. And now, back to the show. Welcome back to Skeptically Speaking. We're on the line with Phil Plait, astronomer, author, and super skeptic. Welcome, Phil.
Hey, I don't know if I'd call myself a super skeptic. That sounds unskeptical to me, actually.
we would call you a super skeptic, if only for your prolificness. So Phil worked on the...
All right, that's acceptable then. All right, go ahead.
No, do interrupt. So Phil worked on the Hubble Space Telescope. His Bad Astronomy blog was actually chosen one of Time's best blogs of 2009, and he's had an asteroid named after him. He is also the president of the James Randi Educational Foundation. And Phil, we're very happy that you could join us.
Oh, I'm really glad to be here.
So before we move to astronomy, could you just tell us a bit about the James Randi Educational Foundation for anybody who doesn't know?
Oh, anybody who's listening to this show and doesn't know about the JRF, come on. James Randi is the man. He is James the Amazing Randi. He is a conjurer, a stage magician, a skeptic. He's part of the original folks who started the modern skeptical movement. And I'm a skeptic because of Randi. I saw him on The Tonight Show in the Johnny Carson days debunking psychic surgery and Uri Geller.
Right.
And it's his life's work to show reality for what it is, to try to show people that these claims that paranormal powers of dowsing and psychokinesis, these sort of things, are probably not true. There are a lot of scam artists out there. And to try to see if any of these things are true by testing them, we have a $1 million challenge to test people to see if they can back up their claims of paranormal powers. And that's what the James Randi Educational Foundation does. We try to educate people about critical thinking in science.
And the $1 million challenge. Now, this is something that both parties agree on, the JREF and the person who is claiming to have, psychic or paranormal or supernatural of some sort claims, powers.
Yeah, when you say it that way, it seems so reasonable. One of the things we do is, okay, we have $1 million. It's sitting with Goldman Sachs. You can look this up on our website. We print out a new list of how much money is in there and what it's doing every month. And it's funny because a lot of paranormal believers say, oh, that money doesn't exist. And it's like, well, talk to Goldman Sachs. It exists. We got it. The deal is if you can prove some claim of paranormal powers or something like that, we'll give you the $1 million. Now, you have to prove it or at least go through a test. And we have a preliminary test and then a main test. If you can pass the preliminary test, you go on to the main test. And we have to agree, both parties, us and them, we have to agree on the protocols. If you say you can predict the throw of a pair of dice 90% of the time, then we're going to throw a pair of dice 100 times, and if you can predict 90 times you get it right, that's good enough for us because that's way above what you'd expect statistically. Now, if you say you can predict the throw of the dice 51 out of 100 times, then we're going to have to throw the dice 10,000 times, or else statistically, it's insignificant. And if somebody says, no, you can only throw the dice once, we'll say no. So, we have to negotiate on these protocols, and both parties have to agree before we move on. So everybody who has ever been tested has agreed to the protocols. And it's amazing, so to speak, how many people after the fact say, well, these were unfair. And it's like, well, you signed them.
Exactly.
We negotiated with you for a year on this or whatever. And it's amazing. So many of these people later say it was unfair, or Randi was giving off negative vibrations, or I forgot that the moon was waxing gibbous, or something like that. They always come up with excuses on why they fail. Very rarely do you hear the excuse of, oh, I guess I must have been wrong.
Yeah, I bet you don't get that a lot.
That's how science works. So,
I find this interesting because we had a psychic on the show a while back, and I asked her...
I'm going to correct you and say you have someone who claimed to be a psychic.
Thank you.
Yeah, there you go.
We had her on the show.
Saying.
No,
okay.
Absolutely. And actually, I use psychic as a profession name. Like homeopath. They're a psychic. So that's what they practice. But what you would call it? She actually answered. I asked her the question, "Why have you not entered James Randi's $1 million challenge?" And she said that she wasn't broke enough yet.
She wasn't what enough yet?
She wasn't broke enough yet. She didn't need the money badly enough. That was her response.
We hear that as well. I don't need the $1 million. I think that through, and I think there isn't a human on the planet that can say that. Bill Gates, if he could do this test in under a minute, that's more money than he can make in a minute, I'm guessing. I don't know. But, it's something like that. There are only a handful of people who can really honestly say that. And some people, so it's an excuse, is what I'm saying. And there are people who are saying, well, it's dirty money. Randi is such a negative person that's dirty money. And I think, well, you know what? then you know what you can do is you can win the $1 million and then give it away to charity.
To a
or
psychic
burn
charity.
it. But, you know, what you're doing is if you really think that we're so evil and awful, you're taking away this money from us. We don't have it anymore. We lose the challenge. We're humiliated, you know, or you know, maybe we're not. Maybe you've really proven that psychic powers exist, and then we're thrilled. That's a whole new paradigm in science if you can prove this, and it's not a hoax of some sort. And honestly, if you're good enough to hoax Randy or some of the other people that we have who help us with these tests because he's the best in the world, then you deserve the $1 million. So, you know, for somebody to make an excuse that I'm not broke enough yet or it's dirty money or whatever, it's an excuse. Come on.
So the JREF's big event is fast approaching. Do you want to tell us about that a bit?
No, I'm done with that. No,
Really?
I'm kidding. The amazing meeting is our annual conference we have in Vegas. I was going to say every year, but that would in fact make it an annual conference. I already said that. It is the largest annual sort of community gathering of skeptics in the world. We bring together people from all walks of life. It's really a tremendous grassroots event. People call it the Woodstock of skepticism. We have great speakers. We have Bill Plait, who's one of the executive producers of The Big Bang Theory, the TV show. We have the usual guys. You know, we have Michael Shermer, Penn and Teller. Randy will be there. I'll be there. Adam Savage from the Mythbusters is a regular. Jennifer Wellett, I'm thrilled to have Jennifer. She blogs at Cocktail Party Physics. She is also a science writer and is in charge of the Science and Entertainment Exchange, which is a National Academies of Science effort to put more science into TV shows and movies. And there are big-time Hollywood producers and directors who are part of this.
Dustin Hoffman is involved in that one, right?
And they're already doing a really good job doing this.
Dustin Hoffman is involved in that one?
Dustin Hoffman, you may have heard of him from The Graduate, right? Yeah, I think he's done a couple of movies since then.
Yeah.
Seth MacFarlane from Family Guy is doing this. Jerry Zucker from Zucker, Abrams and Zucker, Airplane, those movies. He's made a lot of movies since then as well. And so there's a big effort in Hollywood. There are a lot of scientists involved trying to get scientists portrayed more accurately and science portrayed more accurately in Hollywood. And so Jennifer is going to be giving a talk about that, and we have her on a panel talking about science in Hollywood as well. So, you know, it's typical huge event. Of 800 people registered so far. We still have 3 more weeks. It's July 9th through 12th at the South Point Hotel and Casino and Spa in Vegas. If you go to randy.org, which is randi.org, or amazingmeeting.com, you can go there and see our lineup and sign up for this event. I cannot recommend it strongly enough. It is awesome.
And Skeptically Speaking will absolutely be there.
Great. I'm really looking forward to you guys being there, too.
So before we continue, callers, the number is 780-492-2577, extension 1. Or you can email live at skepticallyspeaking.com. Or if you're on Twitter, we're at Skeptical Radio. So let's talk a bit about NASA.
Sure.
They didn't get to launch the Endeavour shuttle on Wednesday. What happened?
No. What happened is the same thing that seems to happen quite a bit. There was at first there was a hydrogen vent leak that was a problem, and then weather came in, and altogether they decided they had to postpone the launch. The problem is they can't relaunch, or they can't launch it until July 11th. It just has to do with the angle of the shuttle when it's docked with the space station, which is where it's headed. The angle of the way the shuttle has to be docked to it makes it very difficult for them to control the temperature on board the shuttle and the space station because of the position of the sun. And it's a strange thing to think about. When I first read it, I thought, that's odd, and then I thought about it more and realized, oh, well, of course. The space station maintains a certain attitude, a certain rotation angle compared to the Earth and the sun, and when the shuttle's docked to it, this particular couple of weeks coming up, they can't control the thermal conditions, so they're going to postpone it. In the meantime, they were able to launch the Lunar Reconnaissance Orbiter, which is now on its way to the moon, and I'm really excited about that because I've been sort of tangentially, I wouldn't say involved, but I've been a fan of this mission since NASA literally announced it years ago, saying we want to do this, help us do it. And so that's great. It's going to go into orbit around the moon on Tuesday and start, eventually after a shakedown, it'll start taking lots and lots of pictures of the moon, and it'll have a resolution of 18 inches. So this thing will really be doing super high-resolution maps of the moon. It's going to be pretty cool.
Phil, you're very popular. Our phone lines are already full. We're going to
Really? Then I won't tweet this on Twitter. Okay.
We'll get right to our first question.
For sure. Nathan, are you there?
I am here.
Great.
So,
Go ahead.
I've got a bit of a Battlestar question for you, Phil.
Battlestar?
Battlestar, yeah. I know that you
I
didn't...
only watched the first 2 seasons, so there you go.
Well, I hope you don't mind too much of a spoiler then.
Okay.
You're going to give Phil a spoiler?
No spoilers. Off air.
Spoiler alert, everybody.
Dude.
I know, I'm bad. Well, actually, it's just about a claim that they made in the last episode.
No, you can't ask. That's horrible.
I can't ask?
I can't say never, but I'm almost certainly not going to get a chance to watch the rest of it.
Are you
I've
sure?
just got
Because
too
we have the
much
button here that
so.
can just kick him off.
Okay.
Are you sure?
I'm sure.
Okay.
All right, go ahead, Nathan.
In the final episode, they had what they called a naked singularity, and that was where the big Cylon base was located, in the accretion disk. I've had some discussions with a couple of friends, like Sean and a couple of the other guys that we know up here, and I argued that the location would not be visible.
So, okay, Nathan, you're a little hard to hear here. Basically, they had a spaceship that was in orbit around a black hole, and he's wondering if that was possible or if the ship would have been destroyed.
Well, specifically, it was in the accretion disk.
Okay.
So it's in the accretion disk of a black hole. Well, if it's in can a black hole have a naked singularity have an accretion disk? I'm not even sure that's possible. But do they ever blow up a Cylon base station in the 4 seasons of the show with missiles? Did they ever actually destroy one? Yes?
Yeah, they
We're
do.
nodding for some reason.
Then,
No, sorry.
you're
Because you
nodding.
can also-
Oh,
yeah,
of course, I
helpful.
should have been able to hear that. All right.
Yes.
So the jelly beans inside your head were rattling. I wasn't sure what that was. Yeah, so if a missile from Battlestar, from the Galactica, can blow up a Cylon base station, yeah, I'm not thinking you can keep one in an accretion disk. Now, having said that, the science advisor for the show is Kevin Grazier. He's a friend of mine. And he refuses to give me any spoilers about the seasons I haven't seen, so he never told me about this. So given that he actually works on the Cassini mission. He helps plot the Cassini probe orbiting Saturn. He helps figure out what orbits the thing is in, where it's going to go. I'm guessing he knows about accretion disks. So if there were some way to do it, he would have figured out a way to do it. So they either had shields or something was going on. I would have to guess. Without having seen the show, I would say it would be very difficult. The accretion disk around a black hole is the matter that's falling into a black hole, and as it falls in, it's circling around the black hole. And the stuff inside is orbiting much faster than the stuff farther away, because the closer you are to a source of gravity, the faster you orbit, right? Mercury goes around the sun faster than the Earth. In the accretion disk, stuff near the black hole is moving hugely faster than the stuff farther out. That creates friction, it creates strong magnetic fields, there's all kinds of stuff going on, and basically the accretion disk around a black hole is heated to usually millions of degrees. And it's glowing in X-rays, and anything that gets close to it would be fried. So I have a hard time understanding how a base station would be in an accretion disk unless, they had some sort of gizmo which kept them alive. But without having seen it, that's all I can do is give you a short lesson on black hole physics.
Great. Well, thanks for the call, Nathan. We're going to keep the line free for the other callers who are trying to get in there. So please call back. It's 492-CJSR, area code 780. Let's do that in the right order.
About more TV shows I haven't seen.
Oh,
Sex in the City and I don't know, Guiding Light.
Can we be skeptical
there's
about
this time,
Sex in the City?
There's this time where Carrie, she's approaching a point in the universe where I don't even know. Okay.
So Phil, you worked on the Hubble as well.
Yeah, for a few years.
Mm-hmm. Actually, did you know that Wikipedia says 5 years, and your site says you worked there for 10 years? Which is it?
Well, okay. I started working with Hubble data in 1990, shortly after it launched. I actually signed on to a project, it was my PhD research, a month before Hubble launched, which was in April of 1990. And then I worked on Hubble data until I graduated in 94. So that was basically 4 years of working on Hubble data. I wasn't involved with the telescope itself. It was just data from the telescope. I worked on another project for about 6 months and then got hired with a new company where I did work on one of the cameras on board, and I did that for roughly 5.5, 6 years. So altogether, I worked with Hubble for 10 years, but 6 years was working, specifically on the telescope stuff, whereas for 4 years it was just getting stuff out of it. So it just depends on how broad of a definition you mean working on Hubble. I worked with Hubble data for 10 years, so I think that's a fair cop. I think it's okay to say that.
You heard it here first, folks. And we have another caller.
Are you there, Ashley? Yeah, we're rolling right along here.
Oh, yeah.
Are you there, Ashley?
Yes.
All right, you have a question for Phil?
Yeah, so recently some friends and I were discussing dark matter, and we were wondering if you thought that this was something that was maybe similar to the ether hypothesis or maybe prior to something like special relativity.
Yes, another easy question. Okay. Dark matter is actually pooped out by Nibbler. Not many people know this. Nothing?
All the
No
real science
Futurama
right
jokes
here,
here?
folks.
Okay, never mind. No, her question is dark matter just a modern-day ether? And the idea being that before relativity, it was thought that everything that moved like a wave, like an ocean wave or an earthquake or something like that, needed a medium through which to move. So sound can move through air, can move through water, can move through solids. And so light being a wave, there must be something in space through which it moves, and they called that the ether. And then it turns out, no, there is no ether. Light is sort of its own medium. It's electricity and magnetism together, and it vibrates through that. And so it doesn't need a medium through which to move. Einstein took this idea and ran with it, and so the ether was relegated to the bin of, old useless ideas like, phlogiston and that sort of thing. Well, dark matter is... Some people think it's the same thing. We've got this idea that we look at galaxies and they're rotating too fast. We look at clusters of galaxies and they're moving too fast. And we think that, the gravity of these objects isn't strong enough to account for this behavior. Well, the idea being that now there must be some matter there that is too dark. We don't see it, but it has a mass. And it's adding to the gravity of these objects, and that explains why they're moving too fast. Well, but you're thinking, well, isn't this just an ether? Isn't this just an idea you're adding on to the mix that you don't need? Maybe relativity is wrong. And a lot of people argue that for a long time, but it turns out, no, dark matter has actually been shown to exist. We've done observations where we've looked at clusters of galaxies colliding. And when you measure very carefully the light coming from background galaxies, you can see the effects of the dark matter on it. And you can map where the dark matter is. And it goes according to the theories that we've had about how dark matter should behave. So the observations are actually backing this up. If you Google the words dark matter and bullet cluster, bullet like a gun, and cluster like a cluster of peanuts. I don't know, a turtle cluster. The bullet cluster is one of these clusters. It was really the nail in the coffin of people who claim dark matter doesn't exist. It really, really shows that, yeah, dark matter's out there. We just don't know what the heck this stuff is. It's not normal matter at all, or else we'd have seen other effects of it. So it must be some new kind of matter that we don't understand.
Great.
So there you go.
All right. Well, we have another caller yet again. I did want to mention our last was from Columbus, Ohio. I forgot to throw that in.
OSU.
We also have Andrew now on from Ottawa. Are you there, Andrew?
Yes. Hi, Phil.
Howdy.
I have a question about something that gets a lot of comments on your blog about when things happen when they're far out in space. So sometimes we have evidence of a supernova remnant from that seems to have been from a supernova about 100 years ago, but it's from a place 20,000 light years away. And so people want to say that happened 20,000 years ago, but I know you like to say that no, it's really a lot more recent. So I wondered if you could expand on what you mean by that.
This is one of those things that I always dread getting asked in a radio interview live, because it's so hard to explain. And I want to write about this. I keep thinking about it, and every time I sit down to write about it, I wind up getting a headache, and I can't do it. So the idea is that you have an object 1,000 light years from the Earth, and it blows up. It takes 1,000 years for the light to get to the Earth. We see it. And then somebody says, this thing blew up 1,000 years ago. And I say, no, actually, it's not really legitimate to claim that. the idea is that it blows up as you see it. It's happening sort of now. And it has to do with very complicated ideas in relativity and cosmology and all this stuff. And I have a really barely tenuous grasp on this as it is. But the idea is that light is the ultimate speed limit in the universe. And it's tied in with the fabric of space and time itself. And so when we're getting our information from some distant object, you cannot get information from this thing faster than the speed of light itself. And in fact, if you look at the equations, it doesn't make sense to say, what is that object doing now if it's 1,000 light years away? You cannot, it's not just that you can't get in your spaceship and go there. It's that woven into the fabric of space itself is this concept that there is no now at that moment. There's all sorts of craziness about simultaneity, about things happening at the same time, and how time flows like the speed of light. And so to ask the question, what is that thing doing now, is sort of a meaningless question, even though it sounds right, because I can say, hey, what's going on now in Ottawa, Canada? And you can sort of synchronize your clocks and have that work out. But for something 1,000 light years away, it just doesn't make sense. It's one of those horrifying things about relativity, like the twin paradox and other things like that, where it's completely counterintuitive, very difficult to explain. In the end, it doesn't matter that much. It's sort of a semantic point. If somebody wants to say, oh, when we see this thing, we're seeing it as it was 1,000 years ago, it doesn't make that much of a difference. I don't argue that point too much. But when you're talking about distances which make a difference on a universal scale, on a cosmic scale, 10 billion light years away, it kind of makes a difference. And so sometimes I'll argue it then. But it's one of these things where basically discussing it just confuses the issue worse. It's not usually the point, so I don't like getting into it much because it takes away from the main point I'm trying to make, whatever that might be. So hopefully I've made things a lot worse by saying that.
Thanks very much, caller.
Thank you.
So,
probably not a very satisfying answer right now.
Callers, I know you're out there and I know you're eager. The number is 780-492-2577, extension 1, and you can call while we go to a break.
Here we go.
On the next Skeptically Speaking, we'll be talking about math. No, really, it's interesting. For example, have you ever thought about what numbers really are? And why pi is cool enough to have its own day? And did you think the chaos theory is simply a butterfly flapping its wings in Hawaii can cause a tsunami in Japan? And did you know that math is the only real universal language? Take that, Esperanto. So let's sum it up together on the next Skeptically Speaking, every Friday at 6 p.m. Mountain Daylight Time, here on CJSR.
Let's get back to the Hubble for a second.
Sure.
We know that the Hubble is the largest space telescope, and it provides amazingly detailed images, and that's awesome. But what would you say are the coolest things about the Hubble that people don't know?
Well, it's actually not the largest space telescope, in fact. It's got a mirror that's 2.4 meters across, about 8 meters. That would be considered 8 meters. I mean 8 feet. Sorry, 8 feet, 2.5 meters. That's actually considered a small to medium-sized telescope as far as ground-based telescopes are. But there are bigger telescopes in space, and in fact, the Herschel Space Telescope, which was just launched by the European Space Agency in May, just took its first light image. That means the first image it took since being launched of the Whirlpool Galaxy, also called M51. It's a beautiful face-on spiral galaxy. That image was just actually released today. I've got that on my blog. If you go to badastronomy.com, you'll see it.
Yeah, it's gorgeous.
And it's a far infrared telescope. It doesn't look at optical light like our eyes do. It looks at very far infrared light to study warm objects and dust and very distant objects. In fact, there's a huge amount of stuff about Hubble itself that a lot of people don't know. There was stuff I was surprised about. Some people are surprised that it looks at the moon. It's actually observed the moon a couple of times. There's this myth that the moon is too bright to look at. And there have been a couple of scientists who have made that mistake, saying it in interviews. But in fact, the moon's not too bright to look at. It's just moving so quickly, it's hard to get a picture of it. But Hubble also looks at the Earth, or it used to, all the time to calibrate its instruments. It needed a really bright object to calibrate the detectors on board. And in fact, what killed me is a friend of mine emailed me and said, "Did you know that once Hubble looked at the sun?" And it did. They pointed it directly away from the sun, and a little rear-view mirror popped out of the back. This is true, and flooded the old wide-field planetary camera, one of the first big cameras on board Hubble. They needed to flood it with ultraviolet light to basically clean it off. And it helps get rid of noise in the detector. And so they observed the sun. There's an image of the sun taken by Hubble. It's not taken by the main mirror, but it was taken by a Hubble instrument while Hubble was in space. And I think that's probably the single coolest thing about Hubble that it's ever done, let alone something that people may not know.
Lovely. I've also actually, first of all, callers again, 780-492-2577, extension 1. So I've heard that we don't actually need projects like the Hubble anymore because land-based telescopes can actually do more. Is there any truth to that?
No.
Just no?
Next question.
All right.
Yeah.
Okay.
No, it's never anything quite simple like that. It's a matter of priorities. I mean, Hubble cost a lot of money, and so the question is, are what we getting out of it that makes it better than a ground-based telescope worth the money? Now, the thing about Hubble is it's above the Earth's atmosphere, and that means that it can see in wavelengths that get absorbed by the Earth's atmosphere, like ultraviolet and infrared. So you cannot observe those from the ground at all. So it's better that way. Plus, the Earth's atmosphere glows a little bit. You know, there's city lights and there's residual glow, fluorescence of the atmosphere, and so basically that gives you, when you're on the ground, a faintest object you can see because you just have to be able to pick it out of that background glow. When you're above the Earth's atmosphere, that glow is gone. You can see fainter objects. And so the really super deep Hubble images, like the Hubble Ultra Deep Field, or an image that was taken by a friend of mine who observed the halo of the Andromeda Galaxy. They sat and stared at the Andromeda Galaxy for days, and he took the deepest image ever taken, at least up to that point. And that couldn't have been done from the ground. Now, the third thing is the advantage of Hubble being above the Earth's atmosphere is the Earth's atmosphere boils and roils. There's turbulence. If you're driving along on the highway and, you know, you see a distant car and the light from the car is all ripply and weird, well, it's sort of the same thing. When you're looking at stars, they twinkle, and that's because the Earth's atmosphere is moving. If you're above that atmosphere, it means you can look at very, very small objects. You can resolve them better because on the ground they're all blurred out from this atmospheric turbulence. There are ways of getting around that. There's a stuff called adaptive optics, where you are literally deforming the mirror of a telescope to sort of compensate for the Earth's atmospheric turbulence. And this works, and it works pretty well. And in fact, there are ways of getting even higher resolution than Hubble, but it's at the cost of not being able to see wide fields of view, for example. Hubble has a wider field of view than will work on ground-based adaptation for this stuff. So it's a trade-off in that case. Eventually, 10 years from now or whatever, yeah, maybe on the ground we'll have higher resolution over a larger field of view than Hubble or space telescopes can get. But for right now, when you put a telescope in space, it's got huge advantages over telescopes on the ground, at least in those areas.
Great. Well, speaking of things you can see through telescopes and detect, we have a question about stellar wobble. So that's when... Isn't this going well for you? all the technical ones. And
now I have a theory about the universe. Okay, go ahead.
So the emailer asks, I always hear that a new planet, singular, has been detected around a star. How can you tell that the wobble is not caused by multiple planets? Is the resolution of the detected motion really fine enough to separate the forces from one or multiple revolving bodies?
Oh, that's a great question. In a nutshell, yes, it is. When a planet orbits a star, the planet has mass. Now, the star has more mass, so you can think of the planet orbiting the star. But in fact, the planet does have mass, it does have gravity, so it tugs on the star as well. And what happens is, as the star is making as the planet's making a big circle around the star is making a little circle as the planet's orbiting it. And that means that sometimes the star is moving towards us, and sometimes it's moving away from us. Now, we cannot see that motion directly. We don't actually see the star making a little circle or moving around. But we can detect that velocity change in its Doppler shift. You know, when a car drives past you and it goes, "Meow," well, that's sound shifting because something's moving toward you and away from you. The same thing with a star. As a star is moving towards us, its light moves up in pitch. It becomes a little bit bluer. And when it's moving away from us, its light drops in pitch and wavelength. It becomes a little bit redder. And it's only, this velocity is very small. It's usually measured in, meters per second, like how fast you can drive in a car, or even how fast you can jog. But we have telescopes that can detect that change. And it's periodic, right? The planet's orbiting the star every 4 days. And so we see this sort of sine curve, the sine wave in the Doppler shift. It's moving towards us and away from us and towards us and away from us in a sine curve. Well, that's how you detect these planets. It works, and there were a lot of people who doubted it at first, but we came up with other ideas to show that this really was working, and yeah, we're detecting these planets. The beauty of that is, once you have you nail down this sine wave, and you say, we've got a planet of this mass orbiting at this distance, you can sort of model that sine wave mathematically and then subtract it from the data. Keep observing the star. Keep subtracting that sine wave. And then if there's another planet in there that's maybe orbiting farther out and it's harder to detect, its signal will pop out. And so you can keep doing this, and that's how they detect multiple planets. By modeling the sine wave, by modeling the way the planet's affecting the star, subtracting that effect off, it leaves the effects of any other planets that might be there. So instead of just a single planet, you detect multiple planets that way. And it's actually, it's incredible. It works really well. I've seen these data, and once you subtract out the main planet, yeah, you can see those other planets popping right out. And that's how we've detected these systems that have more than one planet. There are several systems now that have 3, and I think there's a system that has 4 planets. But I'd have to actually look that up. I'm not sure. But there are several multiple planet systems out there.
That's great. We actually have another caller from Peterborough, Ontario. We didn't catch the name. Are you there, caller?
Him.
Oh, sorry. Hi, caller.
Who's this?
This is Steve, a.k.a. Some Canadian Skeptic.
Thank you very much, Steve.
See, my note said some Canadian skeptic, and I just assumed he meant he didn't catch the name. We use a whiteboard system here.
Actually, this is Some Canadian Skeptic, the blogger, correct?
Yes, I'm familiar with Some Canadian Skeptic.
Absolutely.
Hi, Steve.
Go ahead, caller.
Okay, well, I've always wondered about Mars. We always hear about how Mars has this really, really, really thin atmosphere. I believe it's like 1/6 the pressure of the Earth. And how is it willing or able to get such massive planet-wide storms that can cover up the rovers and make it real difficult for them to get power with such a thin atmosphere?
Right. Mars actually, it has an atmosphere, but it is extremely thin. It's roughly 1% of the Earth's atmospheric pressure. So it's interesting because that just means that if you were standing on the surface of Mars, you would feel 1% of the pressure on you, but that doesn't mean it has no atmosphere at all. And it does have weather. It has it rotates once roughly a day. It's a 24-hour and 30-minute period. So once an Earth day. I mean, of course, every planet rotates once a day. That's by definition. But when we're talking about Earth measurement, it takes about a day plus an hour of Earth days. And so you have sunrise and sunset. It gets cold at night and warm during the day. And you get all the same things that happen on the Earth to make weather. It's just that it has a very thin atmosphere, and so the weather is different in that sense than we have. But it is enough, actually, to generate wind. And when you have any sort of moving gas, it's enough to sweep up the dust, for example, on the surface of the planet. And a lot of the dust on Mars is extremely fine-grained. It's not like beach sand. It's almost more like baking soda or talcum powder. It's very thin, very lightweight stuff. And in fact, I believe it's in the spring as Mars starts to warm up. The winds start to pick up, and it can actually lift enough of this material, even with its weak atmospheric pressure. It's so thin, it can loft this material up into the atmosphere. And when our first probe, Mariner 9, I think it was, Mariner 4, I can't remember which Mariner it was. One of the Mariner series was sent to Mars, and when it got there, Mars was actually in the middle of a global dust storm. And so it actually didn't get very good pictures for quite some time until later when the dust storm went away, and then we were able to get our first pictures from the surface. And so you can get global storms. You can get dust devils. This stuff can dump the sand onto the rover solar panels and weaken their power. On the other hand, the wind can actually blow the dust off the solar panels. That's happened a couple of times. And in fact, I think that just happened to Spirit, I think, that it was losing solar power, but then some winds came along and blew them clean, and now it's up to power again. So, it's the problem when you're trying to rove across a planet with weather. There you go.
Thanks very much, caller.
Oh, thank you very much.
And again, the
Hope
number...
that makes sense.
It did.
Because, I made all that up, so I'm hoping that,
Well, that's why we thought you'd make an excellent guest. You seem to just be able to pull out all the right answers. We'll believe
right.
it.
If it sounds good, that's all I care about, yeah.
It's a logical fallacy there,
Yeah, I know.
All right.
But I'm an authority.
You're right.
Well, we all passed the test. Good work, everyone.
So callers, the number is 780-492-2577, extension 1. And I'm totally going to sneak in a question before someone else calls.
Yes, we both want to hear about...
Okay, so when Kirk and McCoy are on the shuttle... And they're about to head up to orbit, and McCoy says that there's going to be... That if there's a hull breach, the blood would boil within 12 seconds. And you say on your blog that that's wrong. Can you explain?
McCoy does, in fact, say that. But it is wrong. And I got people arguing with me saying, well, your blood will boil. This is interesting. The temperature at which something boils depends on the material itself, like water versus blood, and also how much pressure there is. At lower pressures, water, for example, will boil at a lower temperature. I live in Boulder, Colorado, which is at 1,700 meters, about 5,200 feet a mile, and water here boils at a lower enough temperature because of the lower air pressure that we have to adapt our cooking to account for that. It's much harder to cook rice here than it was when I lived at sea level in California. Right. So you have to account for that. So at zero atmospheric pressure, water will actually boil at room temperature. Water will turn from a liquid into a gas. Well, blood, it's not so easy with blood. Your circulatory system is airtight, and so if you were to go out into space, you won't get that boiling blood myth that everybody talks about. Your blood's not going to boil. But I argue, some people say, well, if I go down into the ocean and come up too quickly, then I'll get nitrogen bubbles in my blood. And that's the same thing. And I say, no, it's not. Because what you're doing there is that you have gases that are already gas dissolved in your blood. And when you change the pressure that rapidly from high to low pressure, that the gases won't stay dissolved in the blood. They form into gas, they form pressure, and it hurts you. It gives you the bends. But that's not boiling. You're just removing gases from the blood. It's actually just condensing them, sort of. Right. So it's not really boiling. It's different. When people say your blood's going to boil, it's not going to boil in the first place because it's an airtight system. But even if it could, it's not the bends. That's two different things.
Okay,
so
we have...
Am I making any sense? Because
yes,
I might as well just be going... No.
I think it's very much like, saying carbonated pop is boiling, right? It's kind of the same.
Exactly. When that's a great analogy. When you open up the lid to a soda, I think you said pop. I don't know what that is. No, I lived in Michigan for years. I used to get in these soda pop arguments all the time. If you open up a bottle of Coke, right, and it fizzes up, that's not boiling. That's just the gases that are dissolved in it coming out. That's all it is. It's a different thing. And there's a billion other myths about going up into space. You'll freeze instantly like Tim Robbins did in Mission to Mars, which was an atrocious movie. But you don't freeze instantly. As a matter of fact, you would freeze eventually, but it would take a long time.
Oh.
It takes a long time for your body to lose the heat radiating away into space.
Okay. I know that we have an email question and we have someone waiting on Skype, but I get one more Star Trek question.
She is the host.
Okay.
Thank you. Okay, so Kirk, Sulu, and the red shirt, they jump out of the shuttle onto the mining drill. And so the ship was still in orbit, and they jumped out, but they didn't burn up. Explain.
Well, you know what? I had this discussion with somebody from TrekMovie.com. We were talking about this because I was writing my review for my blog, and they were going to post it as well. And it occurred to me that the ships are not in orbit. The drill that's being lowered from the Romulan ship is probably tens or maybe even hundreds of miles long, but the only way it can hover over, or can be over the same spot on the surface of the planet, there are only two ways to do this. One is to be in a geosynchronous orbit. In other words, to be in an orbit that naturally takes the ship as long to go around the Earth as the Earth orbits once. So that's a 24-hour orbital period, and that turns out is about 40,000 kilometers up, about 24,000 miles. They are clearly not that high up off the planet. They're only a few hundred miles off the planet. So they must be hovering. And if they're hovering, they're not in orbit. So when they jump out, they're just free-falling down to the drill. Now, they're going to be booking. They're going to be moving really quickly. And so as they do that, you do see that they're rushing through the atmosphere. I don't remember, did they actually get hot? I don't remember. But I don't think they were moving hot enough to burn up. They would just feel some heat. But as it was, they pulled their chutes and were able to stop. That scene was actually a lot more accurate than people give it credit for.
Huh. And thank you for putting so much thought into this.
Well, I thought it was pretty interesting because, I was getting in this discussion, and I was going to write, well, they're in orbit, and so when you jump from a ship in orbit, you're not going to fall, you're going to stay in orbit. And that's when I realized, they're not in orbit, they're hovering. So when they jump, they will, in fact, free fall and fall down toward the planet. Just like jumping off, a building.
Star Trek gets a pass. Brilliant. Now we're going to go to someone on Skype.
And this might be a tough one to fit in right at the end, so maybe we'll do a short, concise answer to this one. But what do you feel is the most? Yeah, I know, eh? Well, it's not technical, at least. What do you feel is the most important area of R&D that we should be focusing on? And I assume they mean, in space, in astronomy.
Wow. It depends on what you mean. I mean, if you're talking about space-based astronomy, the idea of bigger telescopes and more sensitive detectors always helps. And so they're building the James Webb Space Telescope, the successor to Hubble. It actually has a mirror which is going to unfold. It's too big to fit in the rocket, so it's going to unfold. It's like a flower in space, and that's a really good technology. Solar sails would be a good technology to be able to actually use light pressure from the sun to accelerate your ship. Also, I think if you're talking about space travel, I think probably protection from radiation from the sun is going to be the biggest stumbling block into building a lunar base and getting to the moon, getting to Mars. And so I think developing radiation shielding, which may very well just be using icebergs. Ice is an excellent medium to absorb radiation from the sun. And it's also, you can melt it and use it. It's water. And so that actually might be able to play a dual role when we send ships to the sun, when we send ships to Mars and protect them from the sun's radiation. Also recycling, and of course the psychology of being trapped with somebody who has, terrible flatulence for 6 months on the way to Mars. They're going to have to figure that stuff out as well.
Thank you very much, emailer.
Yes. Could you, in a few words, explain the 550 AU Solar Lens Telescope concept mission? That's our last email question. We were going to sneak it in 1 minute.
Okay. The way a lens works is it bends light. Light comes in from a distant source. The lens bends it and focuses it into a single spot. And that's how you can gather more light and focus a distant object. Gravity affects light the same way, but gravity is much weaker. So you can use a massive object, something that's just basically heavy, like a rock or something like that, and if it's far enough away, it can actually focus the light from an even more distant object. We know this works. We have gravitational lensing. We see this from black holes and other things. This is called microlensing. The problem is it takes a long time to focus light, so you would need your lensing mass to be really far away. It's an interesting idea. I don't know how useful it is right now, but it's cool to think about, and anything that's cool to think about is probably worth pursuing in the long run.
And that is about all the time we have. It was completely useless for me to write any questions this show because we had so many callers, which is wonderful.
At time we'll have to do speed round drill fill with questions. It'll be a new game we can all play.
I'll be following him around with my recorder. I'll tell you, I'll stalk you right now.
Yeah, perfect.
Okay, so thanks so much to all the callers and very much to Phil Plait for being our guest this evening.
This is greatly appreciated, Phil. Thank you.
So, audience, if you like what you heard, please do go to iTunes and post a review. And otherwise, we will see you next week on Skeptically Speaking.
Good Good night, everyone.
South America does not exist. The moon is painted on the sky. Things sometimes fall up, but you never see. And everything you believe is a lie.
Dinosaurs were invented by God.